Good morning. Welcome to today's class. We are at lecture 12. We will be talking about common gate amplifier and these examples. So hope everyone had a good Vijay Dasami. Blessings to all of you. Hope you had a good time with your family. We will continue from there on. Right. So today is the 8th of October. Let's look at common gate amplifiers. Common gate amplifier, what does it say? You have the input applied at the source and the output applied at the drain. Let us quickly draw a quick schematic diagram to take the discussion forward. So we have common gate amplifier. Now let us apply two configurations. First, we will apply the regular one, resistor at the drain. You have the V bias coming at the gate at the NMOS device, and input applied at the source terminal, Vin. Vout is taken at the drain terminal. Resistor RD being the drain resistance, supply VDD. This is one configuration. The another configuration, which is in a more realistic sense, will be as follows. That would be the same configuration or schematic diagram where you have the VB connected to the bias voltage at the gate. Then you have a current source, constant current source I1 at the source. Now you have the DC blocking capacitor C1 and the input Vin. Now this input Vin you give through a DC blocking capacitor at the source to ensure that there is no transfer of DC voltage from previous stage to current stage. You have the output V0 taken at the drain, resistance RD. Now this most important condition is you are using VB to establish the bias condition. Biasing of this transistor defines what is the operating region or the DC operating point you identify. Now there are two things here you have to understand. We can study large signal and small signal behavior here. Large signal and small signal. We will be using common gate amplifiers in many applications, and one of the most common application you would see is low noise amplifier. And when you're designing the circuit, say when you're designing it at 5 gigahertz, or you're designing it at say 10 gigahertz, or more commonly when you're looking at the terahertz domains where you're having the 67 gigahertz automotive radar spec, you will see a lot of these designs commonly using the common gate amplifier. It could be a single stage, one stage, or more than one stage. You will see these common gate amplifiers being used for their application. So this is going to be an important feature if you're interested in RFIC design, where you will be working. So let's look at what are the important aspects that you will have to consider while working on this circuit. Now for what happens when you apply a large Vin? When you apply a large Vin, you're directly applying at the source. So what does that mean? When you apply a large Vin, you have to be careful that your Vin, which is going to be source voltage, is greater than VB minus VT, right? So this condition is, what does this condition mean? This condition means that the VGS is lesser than the VGS minus VT or the input. So this means your M1 isn't turned off. M1 is your transistor. M1 is turned off, and when M1 is off, whatever you see at the supply becomes your output. So in that case, your Vout is equal to VDD. So there is no current flow anywhere. Now what happens as you slowly lower down the Vin? As you slowly lower down the Vin, if it enters saturation. So when it enters saturation, you have the current formula that you can apply. Drain current, half mu n Cox W over L, VGS minus VT. So what is VGS? VGS will be VB minus Vn. This is Vs, Vg minus Vs minus Vt, the whole square. Now this gives you a relationship between ID, and when you want to find out what is Vout, your Vout value is given as VDD minus IDRD, right? Your Vout is VDD minus IDRD. So this is ID current here. Now, what is this value equal to? This value will be equal to VDD minus RD times half mu n Cox W over L, VB minus Vin minus Vt the whole square. Small signal gain is obtained if you do Vout over Vin. So what do we do? Delta Vout by delta Vn is equal to VDD, so it's taken off 0, minus RD. Then you get Vin is present here, so in the square. So it will be 2 times, 2 cancels with 1. So this will only be mu n Cox W over L. 2 times is taken out, so it is VB minus Vin minus Vt. Now this will give you a small signal again. Small signal gain. Now we have another value to find out. What is this value? That value would be, what are the other factors that are dependent on Vn? First one is delta Vt by delta Vn. So delta Vt by delta Vn. Now, where does delta Vt by delta V come in? Basically, it is your source terminal, right? The bulk is not connected. So Vin can be effectively written as source to bulk. So that is VSB. And this source to bulk we know is given as eta. Right? What is eta? Gm over Gm plus Gmb. Right? That is taken care of. Now, this is one factor. Another factor that you have is, what is Vout? So this delta Vout by Vin is given as delta Vt by Vin when you resubstitute. This is will be Vb minus Vin minus Vt times eta Rd. Right? You have to multiply both factors. So this will effectively be given as mu n Cox. Okay, the reason why we are doing, we have 2 variables here. One is Vin, one is Vt, other is Vout. So when we do delta Vout by Vin, you will have delta Vout by Vin. So dou Vin by dou Vin and dou Vt by dou Vin. So these 2 terminals, you will have 2 values coming in here. So this is kind of incomplete statement. So you finish this and then complete it back here. So mu n Cox W by L times this whole factor Vb minus Vn minus Vt times this factor is already present 1. Now you take plus eta, 1 plus eta times Rd. So this is effectively given as Av is equal to, this value is Gm times 1 plus eta Rd. Right? So what are the values, feedback that you get, takeaways here? First takeaway is, while gain is higher than common source stage, gain is higher than CS amplifier. CS amplifier gain is AV is equal to GMRD. Right? Here it is slightly more with the 1 plus eta factor. Second, there is no sign here, so it is a non-inverting gain. Non-inverting gain. Okay, so this is the large signal factor that you are working. Now let us draw the small signal. It is the small signal equivalent. Okay, just for your benefit, let us bring back the circuit in picture. Let us draw the large signal diagram for this one. So let's draw the small signal equivalent. We will first remove the conditions that we have and then proceed. So how do we do that? First thing we will start with is, this is the RD. We have the CMOS NMOS device with its bias circuit VB, voltage Vout RD, when you have VDD present here. You take this value, there is the Rout of this device, the saturation region. Then we have the RS, which is going to come in the source terminal. Finally, the VN supply. Now let us draw small signal equivalent. Small signal equivalent, let us bring back our gray box. Right? So you will have 3 terminals. Gate, drain, source. So now let's start filling up. Gate, you have VN. So this is plus minus. So at the gate you have VN. Then, sorry, at the source you have VN. My apologies. This is your RS. And at RS you have next you consider is what is your V1. V1 is VB minus VN. Okay. Then comes your GM VGS. So this is GM1 V1. This is a VGS supply. Then you have R0. Correct. After R0, now in this case the GMB is not connected to ground. So in the case you will have GMB factor also. GMB. Now this, what is the voltage supply here? Bulk to source. So VSB. USB. Finally, you have the RD resistance connected to the load. This is your Vout. So this is current ID. This is IL, and you know IL is minus ID. If you apply KCL here. Right now, what are the things that you have to apply? So what is the supply voltage applied at the gate here? VB. Remember, so this is the other connection that you have. Now find out what are all the values. How do you figure out? First thing is find the input voltage, find the loop here. Apply KVL at the input loop. So KVL at input loop. KVL at the input side. So what do you get here? V1 plus the drop across this Vs plus Vin. These are the three terminals, but each one is taken in the negative sense. So you will start off with V1, then go negative, minus voltage drop across this. So what is the voltage drop? This value, right? V out by RD. This is a current, right? So we'll do it this way. V1 plus ISRS plus Vin equal to 0. Now this IS that we get here flowing here is the same current ID. ID is IL. IL is V out by RD. So if you substitute, you get minus V out by RD times RS plus V in V1 is equal to 0. This first equation. Second, let us have one more loop on the output side. So, KVL at output loop. The KVL output loop, you will again can start from whichever side you want to start. So if you start from here, our output, the voltage drop here across output is equal to the voltage drop across this resistor plus the voltage drop across this resistor plus the voltage drop from the supply voltage, right? So we can just write that. So V out is equal to I R out plus ISRS plus V in. So let us now write I. This I can be written as negative of these two terminals. You'll have to apply KCL here. So that will be minus V out over RD, then minus GMVN, G1 V1 minus GMB V1. I is taken care of. Then same value, minus V out by RD times RS plus V in. So you have V out value, you have V1 value which you will substitute, then separate out the values, and finally you will get the expression V out by V in is equal to voltage gain is equal to GM plus GMB R0 plus 1 whole divided by R0 plus GM plus GMB R0 RS plus RS plus RD whole multiplied by RD. Right? So what do you infer from this circuit again? We infer that it is a non-inverting gain. Non-inverting gain, it has a gain larger than CS stage. Okay, in this case, it is due to body effect. Right? Here, body effect is a desirable feature. Now, in this particular case, we have assumed that the RD is passive. Right? Now, what happens if RD is replaced with an active source? So, RD passive. RD is related by ID, which is a current source. or you can use ID as a diode connected supply, active source. In that case, what will happen? In that case, your RD becomes a constant current source. Then the effective total resistance will change and become only the numerator, GM plus GMB R0 plus 1, because RD will become infinity for ideal source. So the moment this infinity factor comes in, this makes no sense in that case, right? Now, what happens in the same case if there is no GMB value, no channel modulation, or you get a current source? So small signal equivalent with current source based load. Sorry, load current. So let us see how the small signal equivalent will change with respect to that. So when we say RD is current source will go away because it is infinite resistance. Now because that goes away, the impact of R0 is also reduced. In this case here, KVL is not needed. This KVL will exist as it is. What does this become now? In this case, you will apply only KCL here. If you apply KCL at this node, KCL at output node, and KVL will come here. So with KVL, what are the learnings you have? V1 plus Vin equal to 0. And in this case, you will get okay. One other factor which I wanted to tell was the absence of channel length modulation. No CLM. No channel length modulation. This implies lambda is 0. This implies R0 is infinity, right? No channel length modulation. Another factor is constant current source. Constant current source at the top node. So what do you get here? Vin, let's come back again. KVL will be V1 plus Vin equal to 0. What else? KCL when you apply, at KCL I will get GM plus GMB times V1 is equal to minus V out by RD. Or can just keep it here and say V out by RD equal to 0. So if you take these two conditions, you get your AV is V out by V in times GM plus GMB times RD. Or that is equal to 1 plus eta times GM RD. So this again shows that the non-inverting characteristic is present and also the output there. Now there are, as we find out, next we will have to find out what is the input impedance. What is input impedance here? Input impedance, where do you see? Input impedance is seen over here. So what is the input impedance seen at this particular stage? What is the circuit that determines input impedance? We will draw it here quickly. RD. VB, this is M1. There is a channel length modulation is present. So there is an output impedance R0. And this is the input impedance Rin that you see. So what will be the Rin that? To measure Rin, you can apply a test voltage and a test source. Vx, directly apply at this point. This will be Ix. So we will find out Rn as Vx minus Is. So apply again same thing, and if you apply KVL, yes, we have the output impedance here R0. So if you apply KVL in the first loop, you get V1 is equal to minus Vx. Remember, we will have to remove this resistor here because we are biasing using a constant current source. So there is no resistor into the picture. Then what is the other Vx test that we get? Apply KVL in this loop. Right? When you are applying KVL, KVL inside loop, KVL at the outside loop. That you get RD times Ix, total current, right? Plus R0 times Ix minus Gm plus GMB times Vx is equal to final value Vx. Now if you simplify both these and get V in as Vx over Ix, and that is given as RD plus R0 over 1 plus Gm plus GMB R0. Now this, if you can simplify just to get understanding, you can equivalently write it as RD divided by 1 plus Gm plus GMB R0. You can remove this one. So it will be RD by Gm plus GMB R0 plus, now when you have R0 by Gm plus GMB plus R0, you will have R0 will cancel with each other. So you'll have this term 1 plus Gm plus GMB. So few conditions that you can quickly absorb and understand. First thing is, let us understand what are the special conditions that we will see. One of the conditions is if RD is short circuited. What happens is RD is 0. The moment RD is 0, what is left over with this? Take this effective. You have Rn is R0 over 1 plus Gm plus GMB plus R0. Sorry, times R0. And what happens if your RD is a ideal current source? If your ideal current source, RD is infinite. So your Rn will be infinite. So what happens is, if your input impedance is an realistic value, then only you have ideal current source or common gate stage is low impedance. Otherwise, the common gate impedance will always be high itself. So the Rin of CG is low only if the load impedance is low, which is at the drain. If you do any other ideal amplification, you will get Rn is infinity. So you need to carefully understand. So this is the common thing with this. Common stage, right? Sorry, common source amplifier, Rn is always infinity because this input is applied to the gate. In this case, if your load is low, then your Rn also is low. So that is one understanding that you have to do. Now, what is the output impedance? Output impedance you will get from the gain circuit. It is brought here. Output impedance will be 1 plus GMB plus GMB, that is this R0 plus GMB times R0, this value multiplied by the RS. Now that will be in parallel with RD. So this will be your output impedance. Understood? Now let us do a quick example to understand what we have read till now. Because learning by example is my favorite way of learning. So what is the example we can do? We will say for a typical exam question, if you say find out what is the small signal amplifier for this kind of a circuit. It's the first time you are seeing cascaded devices, but this cascade device is familiar to you. What is that cascade device? We have device M2, device M1. At the gate of M1, we will apply the input and RD. If you note, one is an NMOS device, M2 is a PMOS device. Now, what is M2 connected as? M2 is connected as diode connected, right? Diode connected means its effective impedance looking into the rays is 1 over GM. It is in the edge of saturation, so you can use the saturation drain current equation as a load. Okay, and you will also have channel length modulation will also be there. So you'll also have R0. So this R0 is going to be 1 over GM value. So we have to do two considerations. We can do is one in the presence of channel length modulation, another in the absence of channel length modulation. So let us start when channel length modulation is 0. Okay, the question is find the gain, open loop gain in the circuit. Find the small signal voltage gain. Find the small signal voltage gain when channel length modulation is absent and present. So AV when CLM is 0 and AV when CLM is non-zero, that is, it is present. Let us begin. How do we start off with this? First, we need to draw a small signal equivalent. How do you begin with that? When lambda is equal to 0, that's our case 1. Channel length modulation is 0, so lambda is equal to 0, and this is for both M1 and M2. So in that case, what do we infer? M2 will become 1 over GM2 load, right? Small signal load due to the single stage amplifier and is a diode connected load. Now let us quickly draw the small signal equivalent. How does that look? Gate, drain, source. At the source we have 1 over GM2 impedance. This is V1. GM V1. GM V1. With GM you will say GM1. Then you will have lambda is equal to 0, so no R naught. In the absence of R naught, you are only left with RD. Where is the V out taken? Here is a V out. In this case, this V out will be here. Input is connected V in, right? Input is connected at this place. What are the two things that we can do analysis wise? So we'll first apply easiest one to do, KCL. What happens when you apply KCL here? KCL gives you, this is your ID current, this is your IL current. So ID is equal to minus IL. That is equal to V out by RD. And this ID is now equal to GM V1. Right? Minus GM V1. So that is equation 1. So V out by RD is equal to minus GM1 by V1. Next, we have a voltage source, a resistor here. So we will apply KCL here, KVL. So when you apply KVL, what do you get? The supply V in. V in is equal to the drop across these two transistors. So V1 plus IS. What is IS here? This IS is equal to GM1 V1. IS times R, 1 over GM2. So that can be rewritten as V1 is common. So V1 times 1 plus GM1 over GM2. If you simplify and try to get V out over V in, right? V in value, when you substitute here, V out over V in, you will get simplifying, or the right terminology to be used is and simplification. On simplification, you get V out is equal to minus GM1 V1 RD, this equation. And the other equation will give you the V out is equal to minus GM1 RD times GM2 GM1 GM2 times Vn over GM2 plus GM1. Basically, to simplify, GM1 plus GM2 over GM2. So that fraction is here, only Vn substitute. Now, if you take V out over Vn, we'll give you the gain. AV is equal to V out over Vn equal to minus RD. This RD minus RD divided by 1 over GM1 plus 1 over GM2. It is easy to understand this one because now you're talking with regards to the resistance, right? So what is the resistance of the diode? 1 over GM2. What is the resistance of the device given here? GMRD. So you will get 1 over GM. RD is the resistance present here. So it is a ratio of resistance right now used here. Understood? Clear? So this is case 1 where channel length modulation was applied, negative for both. Now what happens when I do the next one? We will work on case 2. What is case 2? Only one device has channel length modulation, other device doesn't have a channel length modulation. So that is case 2. Now we are going to the more practical scenarios. Lambda is 0 for M1, lambda is non-zero for M2. In such a case, what will M2 become? M2 will show a degenerative impedance, and that degenerative impedance is given as 1 over GM2. That is already there, and because of the channel length modulation, you will have a parallel RO2. So this will be the impedance offered by the resistor, effective resistance that comes over here, the source load. So this is replaced as an effective resistance, which is given as 1 over GM2 by over R2. If you look at the channel length or the small signal model, it will be identical, just a small value change at the Vs. So Rs is going to be 1 over GM2 in parallel with RO2. Same GM-VGS, GM1-V1, this is V1. You will have no R0 here for the main device. Channel length modulation is 0 there. Here you will have RT. V out. V in is applied. So this is your small signal equivalent. Again, simple work, apply KCL here. So KCL you will get it as V out over RD, that is strain current, is negative this current here, minus GM1 V1. Now here apply KVL. So KVL will give you this input supply Vin is equal to this voltage drop V1 plus this voltage drop. This voltage drop is given as I into R. I is GM1 V1 R, 1 over GM2 parallel with RO2. Now if you simplify, since there is V1 on both sides, 1 plus GM1 multiplied by 1 over GM2 parallel with RO2. So Vin, when you simplify both of that, simplification gives gain AV, that is V out over V in, minus RD, 1 plus GM1. Instead of just 1 plus GM2, now you just replace GM2 by RO2. So this is going to be the gain. Instead of just 1 over GM1 plus 1 over GM2 in the denominator, now this 1 over GM2 factor exactly having the RO2, the channel length modulation impact coming in parallel over here, right? So this is second condition. So what is the third condition? Right. Third condition looks something like this. In this case, you will have an output impedance here also, right? So this will be RO1. How will the small signal value change in that case? So this will be case 3. Lambda is non-zero for both M1 and M2. And how will that change itself? You will get 2 factors here. So along with this R0, you will get another GMB. GMB V1. So this is the other factor. And here you will get RO2 present here. So what is that value? So we will now begin. So how do we begin? KCL again. If you apply KCL, we have one resistance. We got the second resistance output here. Third is the current here. So what is this ID? This current ID is the sum of all the 3 currents flowing through here. So GMB V1 plus GM1 V1 plus V0 by R out is equal to the current that is flowing here, V out by RD. So this is one equation. Now what will be the second equation? You will have KVL also applied here, KVL applied here. So V is equal to V1 plus, what is the current flowing? The current flowing is the sum of all the currents, V out by RD times 1 over GM2 in parallel with RO2. So you'll have to simplify. And on simplification, what do you get? KV is equal to RD times, so it will be minus RD divided by, in place of GM, you will have 1 plus GM1 plus GMB plus 1 over GM2 in parallel with RO2. This effective RD will now be RD. What it will be? RD parallel with RO1 and RO2. Okay, so that will be the output that you see here. Any intuitive analysis you got? Okay, now this is a diode connected, right? This next example, instead of this diode connection, we will apply a bias, meaning current source. So what will happen there? Let us quickly have a look. Progressively, we will change the example. Example 2. In this case, let us assume lambda is not equal to 0 for M1 and M2. There is VB connected here. There is a bias voltage. So when you have a bias voltage connected, this GM1 will get removed. Okay. So what does it look like? It will only look like a RO2. There is no GM1 coming into picture here. So if you find out the gain, the circuit will now look like one over RD, NMOS device with the input Vin, VDD, and this will be RO2. Here is the Vout. This is the speciality of the circuit. What will happen here? This is the output here that you see. Since this is the load that we are applying and checking the output here. What does this look like? This is a constant current source. So this is R0. When you apply the small signal analysis, what happens? Small signal analysis is very simple for this one. GM1, V1, then there is R0 at the output, R01. Where is this Vout taken? Not at the drain, right? It's taken at the source of this device. So the drain will be shorted. Here, the drain is kind of shorted. Now we'll bring the Vout here. This is Vout. This is RO2. Here is where you apply the input, V1. And this is your gate input supply. Clear? Now that you have developed this, first thing is apply KCL or you apply KVL. Easiest is KVL. By KVL here, this value is the sum of this value to the source. Vin is equal to V1 plus current through this I0 R0 will be given, or this value is Vout itself. That is one equation. Here the other KVL you will apply here. Apply this KVL. What is this value? What is the current and the resistor value? So the voltage across these two are the same, right? GM1, V1 into RO2. Now if at this point, from this point to the current ground, there is R0. From this point to this, there is R0. So what does this mean? R01 is parallel with RO2. R01 is in parallel with RO2. So this is the R. Now what is the current flowing? G1, G1M, V1. GM1, V1, RO0. What is this value is equal to? The value at this node. What is this node value? Vout. So this is the second equation. So if you want to find out from this, what is the GM value equation? GM1 is equal to Vout. You write it in terms of Vout minus Vin. So GM1 multiplied by Vin minus Vout, V1. GM1 V1 times R1 parallel with RO2, R1 parallel with RO2 gives you Vout value, right? So once you get that value, you can now simplify. On simplification, you get what is the gain. Just take Vout to the other side. So your AV is equal to Vout by Vin. That is equal to R01 parallel with RO2. Now, since this term is there for Vin and Vout, you will find them in both in the numerator and in the denominator. In the denominator, it will come along with 1 over GM1 plus the parallel factor, R01 parallel with RO2. So this is your gain. So what did you learn? This 1 over GM1 is only present in this. You're coming from the impedance that you're looking at here. And this is also a ratio of the impedances only. So there is GM1 factor does not play much role. If R01 parallel with RO2 is a very large value compared to 1 over GM, then the effective ratio is 1 itself. It will be like a voltage follower circuit. So gain will be almost equal to 1. Now let us look at what is the R out of the circuit, right? We'll find out what is the R out in a similar looking circuit. Just so that all bases are covered. Find R out. What does R out come here? What is the circuit? NMOS device. NMOS device. VB1, VB2. This is the ground, and this is this node. I want to find out what is the R out. Now let's begin with this circuit. Base is fixed, sorry, gate is fixed, source is fixed. So this is your current source, right? So current source will have RO2 in parallel. So this is our current source. Let us now build the circuit and see what is the impedance. Let's draw the small signal equivalent. What does the small signal equivalent look like? How do we begin? Simple. Start off with 3 terminals. GM1, V1. Then there will be GMB, VBS, which is again V1. Then you will get output resistance RO1. These are all together. Next value at the source. Source you have parallel resistance RO2 at the source here. You are seeing V1 and your input is applied nowhere. There is no input. It's all fixed bias. So this is grounded again. So what do we need to find out? What is the R out? So to find R out, we'll apply a test source Vx having a current Ix. R out equal to Vx over Ix. This is what we need to find. Apply the model here. Find out what is the value. We'll apply KVL here. KVL will give you this V1 plus Ix flows here, Ix also flows here. Ix RO2 equal to 0. This is one equation. Flow apply KVL on the same. So this Ix will now get divided into 3 currents here. So apply KCL at this node, you will get this summation, or you apply the KVL here. So if you apply the KVL, start with here Vx, then sum of these two currents plus this value Vx minus, or we can just sum it. Ix Ix RO2, right? You have covered this portion. Now find out this portion. What is that value? Ix minus these two currents, GM1 V1 minus GMB V1. Right? This current minus these two current is a current flowing through this resistor I. Now that multiplied RO1. So this is this. Now substitute V1 in this circuit with minus Ix R0 2, and then you get Vx over Ix here. So simplification gives you Rout equal to Vx over Ix is given as Ix bring down, so RO2 is left over plus Ix times RO1. Now all the negative terms multiplied by a negative term here, so that will become all positive. What is that positive value? GM1 RO2 GMB1 RO2 times RO1. Take RO1 outside. This will become GM1 RO2 plus GMB1 RO2. So this is the total output impedance. Right? So understood. Calculation is very simple. You just have to understand how to do it. So it's been 1 hour. Let me give you a 5-minute break, and we will start back on an important topic, which is biasing. Welcome back. So now we will talk about biasing. How do you bias using a single power supply? What is biasing? Biasing means placing the transistor in a desired operating space where you can get best performance of the circuit, where you can optimize the amplifier gain, or you can optimize the circuit operation. So bias is you will have maximize the voltage gain. This is one of the main aims that you will work with. So that means your AV is going to be directly proportional to GM. So you have to, second is maximize the transconductance GM. Okay. Now the question is, how is GM connected to transconductance, or transconductance connected to the biasing? The biasing will tell you that GM is directly proportional to 2K times VGS minus VT. So depending on the VGS, you get it. And this is directly dependent on what is the drain current ID. So the easiest way of biasing is to give a transistor a DC path such that a voltage appears at its input or the output. So we know that these are the RD and RS, right? We are well aware. So if the current is flowing ID here, then this plus and minus sign will give you the VDS. And this is your gate supply, and this minus will give you the VGS. So to keep this in VGS, you need a voltage appear here. So voltage can appear if there is either a voltage divider from some supply to here. That voltage divider easily can be created using a resistive network, R1, R2. So this is going to be the voltage value that you appear. Note, since we said we need voltage division, you can also use capacitance also here. Capacitance also can provide voltage division. You just have to remember what is the voltage equivalent that you use voltage supply. Okay, that will be the two ways that you can generate biasing. This is a low current version. It doesn't take a lot of current, but this will, the amount of IR drop that you get across is dependent here. So here current is more, here current is less. Okay, so these are the two ways that you can easily do it. What is the other goal that you have to get? The other goal is maximize the voltage swing. What voltage swing? Output voltage swing. You should optimize the voltage. So GM is related. This would be Rout ID. Okay. So how do you want to maximize the voltage swing? So if your DC voltage is good enough and your drain voltage swing is there, then your drain voltage swing will be cumulative. What do you mean? If your this biasing is very close to VDD, then a very small swing will also saturate. What will happen? Your VD of T will become VD plus VD of T will be greater than VDD. So this is called distortion. So you'll get a distorted output. You do not want a distorted output. You will see positive side clipping here. Close to VDD. Similarly, when you do close to ground, right, the VD of T will have close to 0 plus VD of T. What will happen here? You will see again a distorted output. What is the distortion here? You will see negative side clipping. So how do you understand where does it go? Why is this negative side clipping? Because it enters into the cutoff region. Device enters into the cutoff region. So to avoid this, we should have some biasing value. So to ensure that this VD can be large, if you want to make this large, then your VD has to be small, but greater than 0. So their relationship of VD will be VD is equal to VDD minus IDRD. VD is VDD minus IDRD, and this will allow a large ID to follow through. If you want a very large ID, because if you have a large ID, you get a large gain. So your aim is to get ID is as large as possible. To get maximized voltage swing, you need to have a large ID value. So VD will be reduced. Another thing we have to ensure that the diode is not entering into the triode region, which is this region. To avoid negative side clipping, you don't want one. So to minimize signal distortion, you will need to get minimize signal distortion. You will need to maximize PDS. So you need to maximize this. Maximize the. So these are the one. What is the other thing that you need? Second, one more thing that you will need is, first one is maximize the voltage gain. Second is maximize the voltage swing. Third, you will have to minimize sensitivity. You have to maximize the sensitivity to input, but minimize the sensitivity K and Vt. What is K? Mu n C ox W by L. Reduce the sensitivity to this value, reduce the sensitivity to Vt. So what can do? Since K is operating and MOSFETs are also sensitive to temperature, K is also value of temperature, mu n, mobility. And Vt is also sensitive to temperature, Vt. Now, let me repeat. Mobility directly depends on the temperature. Vt also has a temperature dependence. So you have to make this effectively. This value, this sense K and Vt should not change with respect to temperature. So how do you do that? You have to be insensitive. So what do you mean by insensitive? If you take the differential of these two, it should not be changing. So what do you mean by differential? D ID, differential of ID with respect to K, and D ID by dVt. So differential with respect to K and the differential with respect to Vt has to be minimized. Or try and see if you can tend towards 0, not peg 0, but tend towards 0. So with this, let us do a quick check here. What all do we need? Make ID as large as possible. Make VDS as large as possible, and make Vs or Rs as large as possible. This is what we have seen till now to make system better. Now, if you look at the equation now of this VDD minus IDRS, this is the entirely complete the output side, right? So this is the swing that we are looking at. Now let us write down this in form of an equation and see what does this equation contribute to. So if you take the KVL across the output loop, you have VDD minus IDRD, drain side. Then comes VDS, drop across the transistor. Lastly, we drop across the source resistor. So you just here. Or take all the negative terms to the positive side and then see that the maximum VDD swing is given as IDRD plus VDS plus IDRS. Now, what all can we do as a reference? Now we need to get output gain, right? So maximize AV. Maximize AV by maximizing this term. Maximize AV by maximizing this. Next, you maximize VDS by minimizing distortion. Sorry, you minimize distortion by maximizing VDS. Then you have this IDRS, you minimize sensitivity. You are using degeneration here, right? Remember, degeneration is giving you better sensitivity, better loop gain. So you minimize sensitivity by maximizing this value. But the total of the three is limited by the VGDD. You cannot go beyond what is the maximum supply voltage. So these are the three conditions that we will govern the operation. So biasing the transistor. So in this one, these are your design variables only. This is called the design space. So this is all that you have to play with. What all do you have to play? One with ID, RD value, RS value, and what is a drop across VDS. So R naught value that you see, right? ID into R naught is what you will see. Now what all can we, how all can we achieve that? Right? Now instead of doing this theoretically, let us do with an example. Because example along with the numerical will enforce the idea into your head. Learn by example. That is the best way. So I will redo the same diagram. RD, VDS, RS, 0. VDD. RD, current ID, VDS supply across the transistor, RD, IDO-RS. Here you have biasing transistor, R1 and R2. R1, R2. This will be your VGS value. So this is the design space that you have. Now let us look at an example. What is the question here? The question is, let the K mu n Cx W by L value be equal to 1 milliampere volt square and Vt be equal to 1 volt. We will say determine the resistor values to bias the transistor, bias the MOS device with a DC drain current of what value? DC drain current equal to 4 milliampere. How do you take it forward? So we know what is the VGS value? We don't know. So that is what we have to find. You have all the other values with you? No. Only ID value is given, RD value is given. But what is sufficient here? ID is equal to mu n Cx W by L VGS minus VT the whole square. You know this factor, so let's resubstitute. ID is how much? 4 milliampere. K is 1 milliampere. VGS minus 1 the whole square. Milli gets cancelled. Root will get 2. So you have VGS minus 1 is equal to plus minus 2. You've got 2 values. So VGS will get 2 values here. So what is one of the value? VGS is equal to 2 plus 1, 3 volt. Another is VGS is equal to minus 2 plus 1. How much is it? Plus 2 plus 1 became 3. Minus 2 plus 1 will become minus 1 volt. So which is a more feasible value? 3 volt is going to be the more feasible value. Now let us apply 3 volt. If you need to get VGS as 3 volt, then what is the source value here? You need ID is 4 milliampere. So what will be the value of RS, sorry. Because unless we get that value, we don't know. So even now, if you assume, let's say RS, let's assume RS equal to 1 kilo ohm. Then V of RS, voltage drop across RS is IDRS. That is equal to 4 milli times 1 milli. Right? 4 milli ohm is the ID current, 1 kilo ohm is the RS resistance, that is 4 volt. So this RS value is now 4 volt. So now we you can get VGS. Let us assume VDD is equal to 15 volt. Okay. So VGS is equal to 3 volt is what we got. So that is equal to VG minus VS. That is given as VS is 4 volt. So VG is equal to 3 plus 4 equal to 7 volt. So this value needs to be 7 volt. So now that you know this value, what is the value of 7 volt? We can find the value of R1 and R2 very easily with 15 volts here. So the VG value with respect to this is given by R2 by R1 plus R2 times VDD, which is VDD minus R1 plus R2 is the total current that is flowing. So now we know what is the value that we need. So R2 by R1 plus R2, that side is VG over VDD, and that is given as VG is 7, VDD is 15. Now if you invert these two, you get R1 plus R2 over R2. That is given as 1 plus R1 over R2 is equal to 15 by 7. If you take this one, again simplify, R1 over R2 is 15 by 7 minus 1. So 15 minus 7 is 8 by 7. That implies R1 over R2 is given by 8 by 7. So if you keep the ratio, maintain this ratio, you can keep R1 is equal to 8 kilo ohm, R2 is equal to 7 kilo ohm. So with this, you will get this value correctly. So check. So 7 divided by R1 plus R2 times VDD. This value has to be VG. 8 plus 7 is 15, 15 cancels, VG is 7. So this is the bias. So now this is condition called, this is the bias, DC bias point of the gate. So you apply 8 kilo ohm here, 7 kilo ohm here. This applying these two, you will get a 7 volt at the gate. So since the drain is 4 volt, 7 minus 3 will be 3 volt. Now this is your biasing condition, right? This is the way to do it. Hope you understood. Any questions here? No questions? Then we are going to start another critical topic. My favorite topic in analog design, current mirrors. So what is a current mirror? So if I place a mirror here and I already have a current flowing through here. Now looking into the mirror, I should be able to get the same current again. I can mirror it any number of times. So this circuit which performs this action to only mirror the current coming out, it's called a current mirror, right? That is this function. Now the question is, how do I mirror this current? So what are the conditions to mirror? The VDS or this current devices has to be the same. If you keep the VDS same, if you keep the geometry same, and if you keep the VGS same, right? Keep the VDS same, W by L same, and VGS same, then you have a nice recipe to get same current. Okay, so this is what we want to do. Now, what is one circuit where VDS and VGS is same? Right? Finally, let me ask questions. Who can give me a circuit where the VDS and the VGS simultaneously are same for both the circuits? Can you give me a quick example? Which circuit will enable this? Arvind, Dhanashri, Harshita, Kajal, Chaitanya, Farah, Premateja, anybody? Okay, nobody. Then what is that circuit? We just learned about that. Saying if I have a diode connected circuit, right? Any diode connected circuit. Any diode connected circuit will have these two values same. Remember, right? Drain, gate, source. So here, these two are same. These two are the same. So which circuit you will give you both VDS and VGS equal to be the same? Diode connected. So that is one device which is VGS. Second, we have a diode connected circuit. Now in this current mirror, if you want it to behave as a current source, you need to always have always in saturation. Diode definitely is always in saturation, though it is in edge, but it is always in saturation. So here, that means the device is always turned on. So your VGS is greater than VT, and your VDS is greater than VGS minus VT. So that is definitely true. So what comes next? So your VDS is same, your VGS is same, it is always in saturation. Then you can, how does this mirror reaction happen then? To find out, let's find what is the drain current through this resistor. Right? What is ID? So this ID will be given as VDD minus VDE minus VD divided by R. So that will be the drain current. Now, if we call this current to be as the reference current IREF, then the resistor value required to generate the IREF current through the diode connected value will be given as VDD minus VD by IREF. So this is the resistor value. Now, what do we do with this? We know how much is the resistance that is to be applied. Now, if we need to get an identical current L, right? Now, for example, in this case, if this is Iref, you want to mirror and get a current IL. That means same current needs to flow. In that case, what is the VDD minus Iref that needs to be in both cases? First one is a diode. Using the diode, we will create a similar VGS and similar VDS in the next device. Okay. So, VDD, RD, VD. Now that you have this VGS here, I need to create a similar VGS. How can I create a similar VGS? If I connect the same VGS to these two places, I will get a similar VGS. Come again. If the aim is to get same VGS in both places, I can just simply short these two. Now that will ensure that this gate supply is given here, this source supply is given here. Now what is the advantage? That you have got this VGS is now same as VGS1 is same as VGS2. Another thing, by definition, what you should get, that the VD voltage that you see at 1 will now expected to come at here. Then if you expect this value to come here, then you need to get the same resistor value in this resistor here. So what you can do is this resistor value you can replace here by getting the same value RD. So what does this mean? If you put the same RD value here, then your drop across this RD is fixed. This is going to be the IREF. So the drop across this resistor is IREF RD. The drop across this resistor will be ILRD. Now, if you need, now what is here? This VGS is same. So VGS1 is equal to VGS2 when you short this. Once you do this, here the VDS is fixed here. So the expectation is VD2 should be equal to VD1. To make this equal to VD1, you try and do RD1 is equal to RD2. So by keeping VGS1 equal to VGS2 and by keeping RD1 equal to RD2, you create the same geometry W by L here with the W by L here, right? So VDS you keep change, W by L you keep change, VGS you keep change. By keeping all of this change, you want to expect VD2 to be the same as VD1. And if you can maintain VD2 to be VD1, then you will be able to mirror the same current that is flowing through this transistor into this transistor, right? So that is the intuition. Now, how does that work? There is one important factor that you have missed. You should ensure that the VT of the diode connected transistor is the same as this neighboring transistor. So how can you achieve that? You cannot have a diode value here and here, right? So you can take the same device. This device will be exactly similar to this device. So that way you're taking the same VT device family. Only thing you're doing is connecting one of these devices gate to the drain, to its drain. So that way a diode is formed using the same family of transistor. So you ensure VT1 is equal to VT2. Now when you ensure this happening, then you will try and get the same value. Now using the mathematically, if you can see, your IREF current flowing through this resistor is given as K times or K1 times VGS1 minus VT1 the whole square. Now IL flowing through circuit 2 is given as K2 VGS2 minus VT2 the whole square. Now by keeping the same transistors, we have ensured that VT1 is same as VT2. By shorting the VG gates of these two devices, we have ensured VGS1 is equal to VGS2. So these two are common. Now only thing left is K. What is a variable contact here? K is W by L. If you keep W by L also same, mu n Cox W by L, mu n is common, Cox is common. Only W by L if you keep, then you will get IREF equal to IL. By keeping all of these constant, you can mirror the current from the ref resistor into this IL circuit. So the current flowing to first of the MOSFET will be equal to second here. Now, very important condition assumption is the VD2 is same as VD1 and VGS1 without any drop is coming across VGS2. So these are the two conditions, assumptions on which a current mirror is built. So now you can replace this circuit as a current circuit as long as what are the conditions? They are maintained to be in saturation. The device can work as a current source or a constant current source. And you expect the drain voltages to be the same. Drain voltages to be the same. And what is the other condition that you have to? Saturation. Saturation condition will be VDS is greater than VGS minus VT. So this you should always ensure, and then your circuit will turn to become a current mirror. Now, what are the other conditions that we will have to check? This load resistor, right? Load resistor is expected to control it. See, keeping the same load resistor for both the branches, you control VD. Now, what will happen if this load resistor changes? What is the limitation? The limitation has to be that this load resistance should not vary. And by how much it should not vary? So there is a reference equation that you will get. How do you get that? Let us see. This is called the limitation of the load resistor. Limitation of the load resistor. Now what will happen? First of all, to find out what is the load resistance value, you need to know what is VD2. VD2 is given as VDD minus RL IRF. Correct? M2. This is IRF. RD or RL. VDD. This value is VD2. So VGS2. So with this value, you know VD2 is equal to VDD minus IRF RL will give you this value. Now, what does this value have to be greater than to maintain saturation? VGS minus VT. So VGS2 minus VT2. So this is a relationship that you have to get. Now, what is this VGS2 equal to? VGS1 minus VT1. So these conditions are present. Now let us take these three and build a condition for them. What is the condition for RL here? RL should be less than VDD minus VGS minus VT. So VG1 plus VT1 divided by IRF. So this will be the RL value. Now, we also know that VG1 is equal to VDD minus R into IRF. So this is on the diode side. So this is, you can either call it as VD1 or VG1. So you know that VG1 is VDD RF. So alternatively, you can write this RL factor to be R plus VT1 by RF. IRF, sorry. So VDD minus VG1 minus plus VT1 by IRF. Now effectively VDD minus IRF, if you take, just substitute for VG value, you will get RL should be less than R plus VT1 by R. Now what happens if RL becomes larger? If RL goes higher, if RL increases, VDS2 will decrease. Right? Now if VDS2 decrease, VDS will be less than VGS minus VT. So this will enter triode region. This will be saturated anyways. And if it enters triode region, then IRF will not be equal to IL. And the current source will stop working. So it will be a different load condition. So in this circuit, you should always check that this value does not change in any condition. RL. So you should ensure that the threshold limit of this RL device should always stay less than R plus VT here, the VT device of this device by RF. Sorry, it is IRF. So VT by IRF has to be the limit within which your RL has to be maintained. So the VGS minus VT of this device will give you some activity. Right? Now, we will now try the inverse of it. What will happen for the PMOS circuits in this case? Because same condition, you'll have to understand this will be the VGS. Sorry, plus is here, minus is here. VGS1. Gate to source. Gate source VGS1. Gate source VGS2. Here will be IRF R IL. Now, for like what we mentioned, this has to be in saturation for it to function. And for IL equal to RF, regardless of the value of RL, IL has to be equal to RL here. You should always ensure that this is maintained. So this is two ways where both PMOS current mirror and NMOS current mirror is drawn. Okay. Now this is symbolic of receiving the current from the supply and giving it to the ground. Right. RL. Now this PMOS would be receiving the current from the supply and giving it to the load. So these are the two current source, and this sometimes is called as a source, right? Because you are going to source it, and this is sometimes called as a sink, because going to sink to the ground and you are pulling it from the source. So these are two conditions that we will use. So now you will see that wherever we start using these notations in the diagram, you replace that in the real circuit using the actual transistor in saturation. So this is going to be the bias design. So how do you summarize that, or how do you make it evident? So the way to make it evident is, now that you have current source and the current drain, now you can do a design sign. I have my main PMOS device here. I will put a current sink or a current source. You can call it I. This I you will replace with your actual transistor circuit, and this is your current load RD with a current ID, and your biasing transistors RB1, RB2. Your voltage supply VDD in all cases. Now, what are the other conditions that you have? K and VT. You'll have to take care. So this is the other VGS. This is VDS. So this is the circuit design aspect of a current source. So the bias design maximizes drain current plus drain current stability. Ensure that doesn't change. So what does this mean by stability? Ensure that this device is always in saturation. Because if it moves back into triode, then the current flowing through this current sink and the actual drain current will vary. So it becomes unstable. So having a correct bias design for the current is essential. So how do you replace this circuit? Now you will replace the circuit as follows. Let me redraw, but in smaller size. Right. Next, now you know this is the current sink, right? So load, it is going downwards. So what is the circuit you need? You need to mimic this particular circuit with a bias. So first thing we will do is, you need to get this current sink. So you will start with the reference current. Start with the reference current. First you will connect to the diode condition. Once you connect to the diode, now you have got the Vref. You need to mimic this Vref to be equal to this current I. So you will connect the bias to each other such that the VGS is maintained in both conditions. Drain also is maintained, and then you will get VGS1 equal to VGS2, and this is the exact node that you are replacing. So the current I here the current I that is flowing in this circuit now is being mirrored, and it will flow in this circuit also. So this is the current mirror. Now in this case, let us find the math. So now since this ID current is equal to I, since ID is equal to I, then the VGSs have to be equal. So the VGS will be equal to I by K plus Vt. I is equal to K times VGS minus Vt the whole square. So that equation can be rewritten like this. And now that you get what is the DC voltage. What is the DC voltage? Vg. This DC voltage is given as VDD into R2. R2 divided by R1 plus R2. Once we do that, now you get what is VGS value. You substitute back into this here. So you get Vs, source voltage is VG minus, VGS, VG minus VGS, VG minus VGS. So VG will be given as VDD R2 by R1 plus R2. So VDD times R2 to R1 plus R2 minus I divided by K plus Vt. So this will be your Vs value. So this is the source value that you will have to take care. So where is this source value appearing? Source is appearing at the source terminal. At this terminal, this has to be the Vs value. So this terminal value has to be VDD by R2 by R1 plus R2 is Vg and this current. So this is your source terminal and this is the Vd, and this Vd should appear as this voltage. So when this voltage becomes the same, then you will get the right value. What is the intuition again? Since we are biasing only the current source, drain current stability is not needed. Okay. So for all conditions, ID will be equal to I. Another thing we have to understand that the DC source voltage of these two devices will be the same. So this is Vs of this device, but Vd of this device. So this Vd will be equal to this Vd. So your IDRD that you see in this case, this IDRD that you see should be equal to what? This IDRD should be equal to the VDS of this device. So when the source voltage V2 is numerically equal to the drain voltage D2, the second mode, the current mirror will appear. So what is the condition for that? Condition for that is the voltage must be greater than the VGS2 minus VT2. That is this voltage. You should be ensure that you maintain that VGS1 minus VT1. Ensure these two voltages are present. How do you work for this? What is your VGS1? VGS1 can be given as VDD minus IRFR. So this is your VGS voltage or VD. Same voltage is appearing here. So this minus VT1. So you need this condition to be satisfied for the second transistor to be MOS. Now, this means there is a minimum voltage V min across the current source right? You need a minimum voltage V min across the current source for it to operate properly. And that operation is critical. How do we set that value? The way to set it is this Vs has to be VGS minus VT. But how do we set this value? You can set this value by setting the gate value, right? So you will go from the flow is like this. You need this value to be set. For this value to be set, you need this VDS value to be set. To set this VDS value, you can set the GVG value. So this way, in 3 sets, you start setting the gate here. As soon as you set the gate value, this next value will get set and the next value subsequently will get set. So what is this? How do you set this gate value? Gate value is VDD minus IDRD. but you need some dependence on that circuit. How do you set this VG value there? You know that using this circuit, VGS is VGS is equal to square root of I over K plus VT. And the DC voltage is determined by the two VDD currents of these two circuits. So we should select the circuit in such a way that this VDD IDRT is equal to your VGS value. So what meant is your VG is equal to VGS plus VS. So this VGS plus this VS will give you your VG, and that is given as square root of I by K plus VT plus VGS minus VT1. That has to be your VG value. So if you select your resistors in that way such that this equation is satisfied, then you will be able to set the VG value thoroughly. So how do you set the RD value now? Now that you have set this, how do you set the RD value? RD value has got two criteria. What is one? The drain across this RD value, the voltage should be less than VDD, such that it ensures it is not going into cutoff. Second, VD value has to be greater than VG minus VT, so as to avoid triode. So this condition is to avoid cutoff. This condition is to avoid triode. Okay, so VD has to be within a range greater than VG minus VT, but less than VD. So generally what you do is you set it halfway through, midpoint. Set it at the midpoint. What will be that midpoint? VDD is VDD plus VG minus VT whole divided by 2. So this will be your VD point, halfway compromise. So to achieve this VD, what is the RD value you have to choose? The RD value you have to choose is RD is equal to VDD minus VD over 2, and that will be given as VDD minus, what is VDD? VG minus VT whole over 2. So now you design RD value, R1 value, R2 value. R1 you will get with VG, this you will get with VD. So this VG divides VT and VS. VS you will use to saturate this current source. So all three devices design is completed. So this is what happens in the design. Now let us do an example and then close today's session, just to understand that you have understood how much calculation and iteration might be needed. So let us do an example. Determine the proper values of R1, R2 and RD. VDD. What is VDD value? VDD is equal to 15 volt. This is RD, R1 or R2. A quick information. So people who have not attended today's class will find the midterm exam extremely tough, because anybody who has missed today's session is missing a significant portion of what is appearing in your midterm exam. So please revise this class thoroughly. Once I will upload it end of this week if possible. This is 5 milliampere current, and there is a minimum voltage Vmin, right? This Vmin is given as 2.0 volt. This is the current that is flowing through here. Now, given these conditions, find R1, R2, and RD. Now, let us quickly look at the solution. So the question is, determine the proper resistor values to DC bias the MOSFET the current source is 5 milliampere. Okay, and has a minimum voltage equal to 2 volt in order to operate properly. Okay, what does this operate properly mean? It has to be in saturation, and it has to be the drains VDS has to be greater than VGS minus VT. So this is the condition. Now let us begin the solution. How do you solve this? First one, since I, the resistance flowing to the resistor RD, I equal to ID is equal to 5 milliampere. What does that mean? The VGS should be equal to square root of I over K plus VT. So now we know this value. How much is this? I is 5 milli, K is 0.2 milli, square root plus VT. VT is 1 volt. Milli will go with milli here. So 0.2 is 1 over 5. 5 into 5, 25. Square root of 25, 5. It is plus minus 5, but you will take the positive value. So 5 plus 1, you get VGS value to be 6 volt. Okay. Next. You need to find out what is the DC value. So you know the VGS value, you know VS value. So what is VG? VG is equal to VGS plus VS. VGS value is 6 volt. VS value is the Vmin value given here, saying 2 volt. 2 volt. So that is 8 volt. So VG value is 8 volt. So 8 volt. Now that 8 volt is given, you know what is the VDD value here. So you find the resistors, value of the resistors now. How do you find the value of resistors? We will call them bias resistors. So we can find bias resistor. VG is equal to R2 by R1 plus R2 times VDD. Right? Now that is given as 8 volt. So R2 by R1 plus R2 is equal to 8 volt divided by VDD would be 15 volt. What this gives us? This gives you R2 is equal to, you can consider as 8 kilo ohm, and you can consider R1 to be 7 kilo ohm. Right? So now you have designed the bias resistor, design is complete. But what we can do now, if you choose this value, what will be the current flowing through here? I bias will be equal to V by R1 plus R2. How much is that? 15 volt divided by 15 kilo ohm. This is equal to 1 milliampere. This is a very large current, right? Too large. Bias current 1 milliampere is too large. So what we can do? Reduce the bias current. Let's say I want my bias current, the current drawn through this only to be 10 microampere, right? When I have 10 microampere only, then V by R1 plus R2 is 10 microampere. That means how much is R1 plus R2? V voltage is 15 volt divided by 10 micro. So this will give 1.5 mega ohm, right? So now if you do 1.5 mega ohm and you divide their ratio into 8 over 15, how much do you get? 0.8. So R2 will be, with this information, R2 is equal to 0.8 mega ohm or 800 kilo ohm, and R1 will be 0.7 mega ohm or 700 kilo ohm. Now, both these values are correct, but depending upon what is the amount of current that you want to save in the circuit or burn, you will change your values. Now, the condition that you have to maintain is you can choose any high bias current flowing through here, but you should ensure that this ratio is always maintained. Now, depending upon this ratio, you can go, or if you simplify R1 by R2, you have to maintain the ratio 7:8. So depending upon whatever is the I bias value, you can choose the correct current, right? In this case, we have chosen I bias to be 110 microampere. So with 10 microampere, you get about 800 kilo ohm and 700 kilo ohm as the ratio. If you take 1 milliampere, you get 8 kilo ohm and 7 kilo ohm as the value. Now that you have understood that, now what do you want the drain voltage to be? What is the DC drain voltage? So the DC drain voltage, we have found that VD should be VDD plus VG plus VG minus VT, or the overdrive voltage over 2. Then we said midpoint, right? We will choose the midpoint value for VD. So this midpoint value you will give here VDD plus VG minus VT. Now that value you can write it as 15 plus VG is 8, VT is 1, whole divided by 2. This value is given as 15 plus 7, 22. 22 divided by 2 is 11. So VD will be 11 volt. So if you remember, I have shown that how do I draw this VDD supply. So this is your ground. This is VDD equal to 15. We found VG is nearly half. This is half, 7.5, slightly above is where we got VG. VG is equal to 8 volt. Now we got the drain volt, VD. VD came between these two, 8 minus 15. If you see, between these two limits, correctly midway. That is what we did, right? 15 is this value. 8 minus VT is VG, this value. Here VD. This is 11 volt. Now that you have found out what is VD, what is the value of the resistor? Resistor value, load resistor value. Resistor value will be given as RD equal to VDD minus VD divided by ID. That value is given as 15 minus 11 divided by 5. That is equal to 0.8 kilo ohm. So in this case, what is your bias point? Your swing voltage. Since your gate is here, minimum value Vmin. Vmin is equal to 2 volt. Right? So this is your Vs. Right? So how much is VGS? VGS is 6 volt. Now VD is here. So what is your swing that you will get? Assuming the swing, the maximum swing you will get is, if you apply a sinusoid voltage, 11 minus 3, you have a 3 volt swing here, VG. On this side, you have a 4 volt swing here. So your input can swing at this range output. Okay. So this is VGS minus VT as a rate. So VG minus VT, 3 volt is what you will get swing here. So hope you understood. Now, where have we reached? We have reached the bias current design as follows. So a circuit biasing will look like this is your 5 milliampere current having a Vmin equal to 2 volt. Then your V bias resistors (700 kilo ohm, 800 kilo ohm), VG, VS, VD, RD 0.8 kilo ohm, current through this bias resistor IB 10 microampere, current through this device 5 milliampere, total supply voltage 15 volt, ground connected 0 volt. So this is the actual complete circuit design M1. Only item missing here is what is your W by L. Right? Now how do you find W by L? You have given K value is 0.2 milliampere per volt square. PT is 1 volt. Right? So from this you can get geometry of the device, W by L. So you know mu n Cox W over L is equal to K is equal to 0.2 milliampere per volt square. So from this, if you get to know the value of mu n Cox, you will get. So now to find this variable, you have another variable ID, which will give you half mu n Cox W over L VGS minus VT the whole square. Right? So ID is there, 5 milliampere, VGS minus VT, 6 minus 5, 5 is there. So ID minus these two, you will get this value. Essentially, it will reach up same. So there is no way of finding W by L without knowing mu n Cox value. So when you get the mu n Cox value, then you can identify the geometry of this M1 device also. Right? So today we covered, let me quickly summarize today's class. So in today's class, we learned first what do we do is we learned what was a common gate amplifier. Common gate amplifier. What did we learn there? We found that its gain is given as GMR0 1 plus eta, and this is greater than common stage gain. common source amplifier gain. Second, the input impedance is directly dependent on the load value, load resistance. If there is no load resistance, then it is infinite, similar to what was in common source stage. Next, we learned about DC biasing of MOS device. Finally, we learned what is a current mirror, what are the values of current mirror, and how a current mirror can be used as a current source. And how we can use this current source to be an active load, and how do you DC bias the current source. Right? So this is the summary that we learned on 8th of October. So hope you will relook into this lecture and read back. So glad to see students all stay there. So why don't you all come in for our class photograph?